My name is Renee Boere. I am Emeritus Professor of Chemistry at the University of Lethbridge in the Department of Chemistry and Biochemistry. Lethbridge is located in the province of Alberta in Western Canada. And I'd like to share with you this presentation called NoSpherA2 for routine chemical crystallographic refinement. Based upon my experiences. It's a video that is based upon a modified version of a presentation originally given at the American Crystallographic Association meeting earlier in 2024. And on this slide, I present to you the outline of the topics I'd like to go through in this presentation. I've turned off the video so that you can see all the screen content and it won't be blocked, but I'll follow along as we go through this presentation. So let me start first of all with my own experience with using NoSpherA2 and OLEX2. This dates back to the online webinars that the Rugaku Corporation started during the COVID-19 pandemic. And they started the Rugaku Practical Schools for Crystallography, which have been ongoing, and also ran some advanced schools, at least one advanced school for crystallography during the pandemic. And these were a wonderful learning opportunity and also opportunity in the situation we found ourselves in during COVID-19. And in those presentations, both Florian and Horst from OLEXis gave some presentations that mentioned the development of this NoSpherA2 software. And the presentation by Florian is still available at this YouTube link in the YouTube channel that belongs to OLEX. And I encourage you to watch that video, which has much more details than I can give you on the theory and the methodology. Then at the end of 2020, there was a publication, an important publication in Chemical Science, where the NoSpherA2 method was formally introduced, and this article gives all kinds of background information and theory, much more that I can give in this webinar. So I encourage you to look at that article and read it before you try to implement the method yourself, should you be interested in doing so. Now, we started out then in early 2021, again, under the conditions of the pandemic and being isolated and not having a lot else to do with our time. And I had at that time this a series of crystals that were available. The first project was this one here that is shown at the top, the one in crystal growth and design, where a graduate student, Flavia, made a whole series of compounds and group crystals, and then I did most of the crystallography. She learned to do some crystallography at the time, and I kind of talked her into trying out NoSpherA2 since we kind of had time in our hands, and she agreed to do that. And then that was in the very early days of NoSpherA2 when we were dealing with the 1.3 release of OLEX2, and we ran into a few roadblocks, but basically the new software was being improved on a kind of a daily basis. And as we worked our way through our structures, more and more of them became feasible. By the end of the time, we were able to do a whole series of structures and get them all successfully refined by this new methodology. And that was kind of really a lot of fun. And then that was followed up by this paper with copper sulfate hydrates, and then later on this paper of some organic examples. And I want to highlight here Flavia, Nathan, Elora, and Michaela. These were all students in my lab who were involved in the this early implementation of NoSpherA2, and particularly Flavia and Nathan, who did a huge workload in trying to in analyzing the structures, because we set out to analyze these structures. And since then, we've published other more normal papers that use the method, and so I think about 10 papers altogether where we have successfully published structures with NoSpherA2. Now, the point of this exercise is that we set out to try out and see if we could do it. So what I'm presenting you today is our experience from largely independent work. Now, we did get assistance, and both Florian and Horst gave great support, very rapid response to emails if we ran into issues and problems, so we got help. But we absolutely did not want this to be an Olexis project. We wanted it to be our project. In other words, we wanted to test whether us, a pretty ordinary chemical crystallography group, also involved in synthesis, so essentially part-time crystallographers, whether we would be able to do this. And at that point in time, that was very much of a big if. And I'm very pleased to say that it worked. And I think the reason that it worked is that this NoSpherA2 implementation in OLX2 is such a fabulously written piece of code, and the whole approach to it is so sensible and well explained that I feel I can be confident in implementing the method. And that's the confidence I'd like to share with you in this presentation. Now, there are some central notions underlying quantum crystallography that we need to be aware of. I'm not going to go into great detail of the theory, just enough to kind of set the context for what I'm talking about, and you'll have to read further. And the place to read further are in the, I would suggest you start with these 5 titles. One of them is the one I've already mentioned, this key introduction article by Florian and his many co-authors that really set the stage for this method. But then these other articles are also very, very important to set the context of what's going on here in the modern thinking and application of quantum crystallography as it is applied to chemical crystallography, or even routine chemical crystallography. Oftentimes, synthetic chemists can act as if this R-value equation is really the most important equation in crystallography. Now, of course, it's not, but it is often perceived to be the gatekeeper equation. With this, I simply mean is that in order to publish an important new work, the crystal structures have to have an R factor of 5% or less, or they just won't fly. Certainly not in JACS or Nature Chemistry or some journal like that. Well, that's not entirely true, but I'd like to just use the R-value equation once again in a little bit of an explanatory context of what we're talking about here. In the X-ray diffraction experiment, we have a crystal which is mounted geometrically right about here, and it is impinged by an X-ray beam, a focus beam that is monochromatic, single wavelength, and then the electrons in the crystal scatter the X-rays to a very small extent, but intense enough that they can be detected. And each of these spots here on this area detector represent one unique scattered wave, which is identified by the geometrical indices H, K, and L, the so-called Miller indices, and that is tied into a geometrical formula, which I'm not going to go into the details here, but it underlies the whole picture as well, greatly simplifying this. And each of these has a unique intensity associated with it. Now, that intensity is associated with something known as the square of the observed structure factor. And I'll explain a little bit more about what that means. But do notice the relationship intensity varies as square of structure factor, whatever the structure factor is. This is highly reminiscent of what happens in quantum mechanics, where if we have a wave function and we square it, we get electron density. And I would suggest to you that that parallelism is not accidental, and therein is the link to quantum crystallography. That's the experimental measurement. But to get a structure, it's a bit of an involved process, and I'm greatly simplifying it. The procedure, nevertheless, always involves building a model. So crystallography, or structure determination crystallography, is always done on the basis of model building. And the models are built using something known as the calculated structure factor, which is a mathematical formula, again indexed to the geometrical Miller indices, H, K, and L. There is a phase correction, which I'm not going to talk about, and that there are other things going on in this puzzle. But once you get the right structure, you then adjust the parameters of that structure, the bond distances, the bond angles, etc., the positions of the atom in the unit cell, so that FCalc changes in order to become more like the FOBS. So FOBS is a fixed entity from the experiment, a series of numbers, essentially, a large table of numbers, and those FOBS have to match the FCalc that we come up with. And that's where this R-factor equation comes from, which is simply the statistical or weighted statistical comparison between the experimental data and the model system. And that's how crystallography works. Again, greatly simplified. I just want to get to some of the issues that are relevant to this presentation. Now, we have just recently celebrated 110 years of X-ray diffraction just a couple of years ago. The first experiments were done in 1912. So we've had about just over 110 years of X-ray crystallography. And during most of that 110 years, most of that century, for sure, the first century of crystallography, the focus of everybody has primarily been on the experimental side, on getting the best possible value of FOBS. First of all, this was done in university laboratories by researchers building apparatus and trying to improve on the techniques and the concepts involved. And then later on, that was just taken over by superb instrument manufacturing companies who deliver to us the beautiful instruments that we have today. And of course, there's also things like beam lines for greater intensity and specialized experiments, etc. But as the technology has improved dramatically over that century plus of development and focus on FOBS, the attention to the FCalc part, the model component, has not kept pace. And that argument is made very clearly in this chemical science article. So again, read that article for the background. But we really have not been changing this model at all over that period of time. And it's come to the point now where the data that we measure almost always contains more information than our model is actually capable of receiving. So we are building expensive equipments, going to visit beamlines, getting superb data, and then we're kind of throwing it away. And that is why we should be concerned about changing or improving the approach to the model. Let's go into a little bit more detail. And again, I'm trying to keep it super, super simple so you can focus on the key issues here. But let's talk a little bit about what this FCalc is. The FCalc then is essentially an attempt to estimate what the intensities should be at each diffraction point in terms of the structure factor. And it's important that we work with the structure factor because it is a phase rule. So it's a summation over every one of the atoms J at its position xj, yj, and zj in the unit cell lattice, multiplied by this 2 pi I, which makes it a phase characteristic. And modified by the geometrical parameters H, K, and L, so that we can measure the impact for every possible kind of diffraction event, every individual peak on that detector is treated in this summation. And similarly, for every atom, there is a multiplier called Fj, which is known as the atomic scattering factor, and used to be called the form factor, why it's given the symbol little f. Okay, so little f is each atom, big F is the complete ensemble of atoms in the unit cell. That's the basic idea behind this. Now, the geometry comes into the picture here again, because for every H, K, and L, every Miller indices, there is a unique angle of diffraction. That angle of diffraction is given by the angle theta, but we usually work this out as sine theta over lambda, so we make it source independent. We can change the wavelength, as it were, and still get the right answer. So everything is indexed to the wavelength and made wavelength independent. And this is an integration which involves the electron density at some distance. That again, that distance is determined by the geometry. Okay. Now, this complicated integration can be explained graphically by this this graph here, where we have indexed the F value as a function of the diffraction angle, sine theta over lambda. Now, at zero, we have what's called the direct beam. So there are zero angle of diffraction, and there we get values for the atomic scattering factor that correspond to the number of electrons, the total number of electrons. We measure all of them in an X-ray diffraction experiment. So oxygen has 8, chlorine has 17. Okay, but these curves fall off with increased angle, and you also have to recognize that as you go up in increased angle of diffraction, you are also increasing the order of the diffraction. So we're going from first order, second order, third order, fourth order, and it's well known in optics that higher order diffractions fall off. Now, there's a rational explanation in crystallography why this intensity falls off with angle, because as you increase the angle, the ejected electron, which induces the X-ray re-emission photon from the L to K transition, that photon at a high angle will pass through the remaining electrons, the remaining core and valence electrons of the atom. And during that directional scattering, it is partially reabsorbed, and that's why it loses its intensity. So the higher you go in angles, better it goes. Now, the other thing to note about this sine theta over lambda is that it becomes increasingly difficult to measure the data, because the intensities get weaker, and you also need shorter wavelength radiation to go out to the extreme of these settings. So the earlier part of these graphs is quite important. Yet, even in the early parts of the graphs, notice what happens here for this purple and this red line. This number 18 corresponds to the atomic number of both the chloride anion and the potassium cation, because they've either lost or gained an electron. And so at the direct beam, the intensities of a chloride and a potassium are basically identical. But notice that the fall off is not identical, so that as you get down even to a smaller value as 0.2 on the sine theta over lambda curve, the purple line is almost dropped down to match the green curve, whereas the potassium remains different. And that although they have the same number of electrons, the two species, they have a different arrangement and energies of their shells, because they have different nuclear situations. More potassium has more protons, and so that the profile down here changes significantly. And so the effect of charge is important. There is another factor going on that's relevant to crystallography, and that is this second term that's added here in the adjusted structure factor. I should have put a little star on the F here, but this is a structure factor which has been corrected for the influence of the motion of the atoms or vibrations of atoms in the lattice. And that is the second curve here. You'll see the second curve, the one that is corrected by the Debye-Waller factor, falls off even more rapidly and quickly kind of bottoms out here and tells you that no matter how, even if you go higher in your sine theta over lambda, you're not getting any more information. That basically says that vibrations of the atoms cause the scattering to become more and more diffuse the more they vibrate. And of course, this is one of the reasons that we routinely measure single crystal X-ray structures at low temperatures. We reduce the temperature significantly, like to 100 Kelvin, so that we reduce the vibration of the lattice, and that helps keep the intensities up, and we can get to higher these values. The reason to go to these higher values is that they are associated with the improved precision of the structure, particularly for the heavy atoms. Okay, so we now have these superb instruments. This is the University of Lethbridge Rigaku supernova. It has two different kinds of X-ray sources. We don't use them at the same time, but we can switch to them very, very easily and under computer control. And here we have this HPAC detector, which is a superb way of counting scattered X-ray photons. And this instrument is probably 100 times better than the instruments of the 1960s. And yet the model that we're using is based upon the same spherical atom approximations that were used in the 1960s. It's important, therefore, to go beyond this model because the atomic form factor, Fj, is charge dependent. I've showed you that a neutral F atom is not identical to an F minus atom in its form factor, but it's not just these gross charge differences. Every different fluorine in a molecule will have a different partial charge loading. That's one of the fundamentals of chemical bonding. So partial charge variations are also significant because the full charge changes so large. Partial charge variations are still significant, and particularly they are significant for the low resolution data. And this is also explained in this article here. So even with copper radiation, which only goes out to about 0.8 in sine theta in the resolution equation, so relatively low in sine theta over lambda before it runs out of steam, then you still get most of the variation due to charge between fluorine and F minus, for example, out here. And you can see that even if you had, say, 10% variation in charge, you'd get significant differences in the form factors here, and that will change the measured intensity of the peaks. Now, the spherical atom or independent atom approximation simply ignores that variation. We simply use neutral atoms throughout in our structure determination. The consequences of that can be shown by this graph. So here we have a fully completed crystal structure of sucrose, and the green mesh there defines the assigned electrons in this structure based upon the atom count. So these are the fully assigned electrons, somewhat adjusted for the asphericity by the vibration of the atoms, but that's them. They've all been assigned to those atoms. But the atoms have other electrons, some involved in chemical bonding, others involved in lone pair structures, and when you ignore those, there will have to be residual electron density. That residual electron density will be both positive, okay, where there is unassigned electron density, and negative, where we have over-assigned the electron densities because you don't have the full charge on those atoms that we've assigned to it. And so this is called an observed minus calculated difference Fourier map, and it shows that there's a residual electron density left over even when you have completely finished your crystal structure analysis. One consequence of this ignoring of the true distribution of the electron density by using spherical atom models is that we need a weighting factor. A weighting factor essentially is a fudge factor that tries to accommodate for this unassigned electron density in a resolution-dependent fashion. And the third and very important consequence to our R factor equation is that they simply can't go to zero. In fact, as I told you earlier, a good structure is one where R is less than 5%. And if R is less than 5%, that means we're only 95% accurate when we're all done with the best possible data and modeling. Okay? And so what NoSpherA2 does is it uses quantum crystallography to get beyond these limitations, and now I'm going to explain how it does that. First of all, it is implemented within the OLEX2 GUI, fully integrated within that software. You don't have to install anything new, although you do need to have access to quantum mechanics software. The following flowchart shows the so-called Hirschfeld atom refinement process as it is controlled by NoSpherA2, and is a visual representation of what happens. Now, this flowchart was developed by Florian Klemes in this shown in this at this website, and also for his YouTube talk, where if you follow that along. So what we have here is, in this box here, OLEX2 itself. And this can simply be a conventional crystallographic refinement engine working here. We can be using shellac, so we can use OLEX2 Refine or some other refinement engine here that is doing standard refinements using these spherical atom approximations. But if you implement NoSpherA2 within OLEX2, then the software will come to the best possible results from the independent atom model, will output that geometry as a CIF file. NoSpherA2 will extract from the CIF file a Cartesian coordinate listing that is compatible with quantum mechanical software, the various softwares that are supported by the NoSpherA2 software. That then sets up and runs a DFT calculation where we are doing a wave function calculation, and we are computing from that an electron density map for that molecule. Okay, and there are two files, WFN and WFX, associated with it that output the electron density based upon the quantum mechanical calculation on the structure that comes out of the independent atom model. Then up here is the main activity of NoSpherA2. It is the Hirschfeld atom partitioning software that takes that electron density and uses the Hirschfeld atom methodology to break up the electron density and assign it to the individual atoms. But now for each individual atom in its true location and its true bonding environment in the molecule in the crystal lattice. That outputs a tabular form of the structure factors, the form factors, that is in a format that can be read by OLEX2 and will replace the normal input of the independent atom model. And then OLEX2 will run through OLEX2 Refine, an improved refinement of the structure where we are incorporating now the corrected and much closer to reality structure factors, form factors for the individual atoms. Now, when that procedure has completed and you now have the next best possible structure, you've optimized the refinement based upon these customized aspherical form factors, then the process can be repeated and in a cyclical fashion, and so that at each calculation of the new form factors, we then re-optimize the structure, improve it again, improve it again. So we are doing a convergence in the calculation of the form factors, and we're also doing convergences within the matching of the F-ops and the F-calc. So we're doing a double convergence, one here and one here, until you get the best possible result from that. So the conception is very similar to standard crystallographic model building. Now, it's very important that we have clarity on what NoSpherA2 can achieve. Let's start with what it is not. First of all, it is not a magic fix for poor quality diffraction data. In fact, it's really for good quality diffraction data. There's definitely an important role for identifying compounds from marginal crystals, and modern technology and the increased brilliance from copper K alpha and rotating anode sources is a real advantage here, so that we can get structures that simply could not be measured in the 1960s from the new hardware. So we are pushing the boundaries, the limits of what's measurable. But some of those crystals have very poor geometries, and they are useful for chemical information, but they are not useful for accurate bond distances and angles. And in that scenario, NoSpherA2 plays no role. The second point, and the most important point of all, is that NoSpherA2 does not produce a computationally invented structure. We are not doing ab initio structure modeling here. The role of the DFT calculation is to calculate what the atomic scattering factors are closer to what they actually are, greatly improving the structure factor. So that is what it is. We use DFT methods to calculate accurately polarized atom scattering factors for each atom in its unique environment. Now, in doing so, we can use relatively undemanding calculations. We can use the easier and faster versions of DFT, and most importantly, we work on the structures generated by X-ray crystallography. We are not doing the time-consuming optimization, the multiple cycles of optimizations used in ab initio structure calculation. We are simply calculating the electron density from the wave functions of the structures as it's given to us. And that is a doable procedure in real time. You can do this on a simple laptop even, and you don't have to wait for days and days to get results. NoSpherA2 uses ordinary crystals with good quality data sets to get more accurate crystal structure models. That's it. That's what it does. Now, by doing that, it is better able to use that electron density that is determined by our superb diffractometers. So we are now able to use accurately measured experimental electron densities because we are theoretically taking into account the electron densities of the molecular structure. Now, a key advantage of using this accurate polarization of the atomic scattering factors is that it is now possible to place the hydrogen nuclei accurately. The independent atom model must place the hydrogens deliberately in the wrong position, because the theory demands that the nuclei be at the center of a spherical electron density distribution. And no bond to hydrogen obeys that rule. All bonds to hydrogen are highly polarized because it doesn't have any core electrons. And so the independent atom model must put the hydrogens in the wrong position. But by allowing for the polarization of that bond in our theory, NoSpherA2 is able to place the hydrogen atoms where they truly are in the molecule. Moreover, the ability to compute those hydrogens more accurately also enables the possibility of full anisotropic hydrogen atom displacement refinement like we normally do for the heavy atoms, so long as the data is of sufficient quality that we can measure enough data to maintain a reasonable data to parameter ratio. It's also worth thinking about where scattering factors come from. Originally, they were determined empirically, simply from the varying responses of standard samples and measuring the decay of the intensity with sine theta over lambda. So it was originally an empirical factor. But as early as the 1950s, it was recognized that self-consistent field SEF computations, that's to say old-fashioned quantum mechanics, was able to get better values for these form factors than you could get from empirical measurements. So, for example, in the international tables, we have this particular table, the intensity of diffracted intensities. These are tabulations for each of the elements of their form factors as a function of sine theta over lambda, and they are used by several different crystallographic refinement softwares. But if you look at the fine print, it'll tell you that they are calculated using relativistic Hartree-Fock or Dirac-Slaughter wave functions. And that just simply means that we've all been doing quantum crystallography for the last 50 or 60 years, but most of us weren't aware of the fact that we were doing so. But we were using that on the assumption that the atoms are spherical and that each atom of the same element is identical. That's why it's called the independent atom model, or perhaps more usefully, the spherical atom model. Not only is the electron density spherical, but all hydrogens are the same, all carbons are the same, all molybdenum atoms are the same in the molecule. Now, this is a very effective, extremely robust, and reasonably accurate approach that is so robust that we can get structures out of those really terribly marginal quality crystals and still get some sort of a meaningful structure out of that. So it's not to be knocked. It has its role, yet it is a rather crude approximation. I try to explain this to my students by saying it's like the ideal gas law is to thermodynamics for crystallography. So, as you all know, the ideal gas law, has been known for about 200 years, is known to be inaccurate. And at best, it's about 1% accurate. But it is such a simple, robust theoretical model that most of advanced thermodynamics is based upon the ideal gas law, and then they do some corrections from fudge factors after the fact to get to more accurate values if they're needed. And it's somewhat similar with the independent atom model. It works really well. It'll probably always be with us as this kind of foundational method, but it is just like the ideal gas law, an approximation, and sometimes a rather crude approximation. If you want to get in some more background on this whole idea of being able to measure very poor quality materials and still get meaningful chemical structures from them, I encourage you to read this article by Amber Thompson. So that'll help put that into context. And I also want to emphasize the importance of crystal structure verification, that's to say the CheckSIF routine. This is also often perceived as a barrier, something holding us back from publishing our structures. But the real purpose of CheckSIF is to just ensure that the accuracy is sufficient to the purpose. But the purpose can vary. That's what Amber talks about in this article. But whatever the purpose you want to put your structure to, you must know with confidence that you have the accuracy that is sufficient to get there. And that's what CheckSIF really is all about. Okay, here's my first practical example. This is HAR NoSpherA2 implemented on some crystals from organic crystallography. Now, these compounds are a series of organonitrile valence isomers published in that paper I mentioned earlier. For example, we have this crystal structure. This compound was made by a colleague of mine who did all the chemical characterization and drew beautiful crystals of his compounds, but simply wasn't able to use X-ray diffraction on them. Some of these compounds are quite old. And I convinced him to allow me to measure the crystal structures, and he graciously agreed to that. And so we got the structures, and we were really thrilled. I mean, we're talking getting an R factor of 3.3%, pretty small difference map. This is a totally publishable structure by all accounts. Okay, we'd be happy and thrilled to have it. And yet, when we put this into NoSpherA2, we get the R factor goes down by a factor of 3, and the background electron density map is improved by a factor of half. It's 50% better. Okay, and it's a little bit subtle from the picture here, but you can see that now we have all the hydrogens at their true CH bond distances, depending on the relative hybridizations of the carbons, and all the hydrogens have the anisotropic displacement parameters, just like the heavy atoms. So that rather than omitting the crystals, the hydrogens from the structure picture for clarity, we can now display the hydrogens for accuracy. And I think that's rather the better way to go. Here's a second example. Again, a very good structure in the IAM, but when you implement NoSpherA2, the R factor goes down by a factor of 3, and again, we're having the background electron density map intensities, so a much better structural result. Then we've done this for 14 similar structures, and I won't bore you on the details. You can read the paper if you're interested. But let's focus in on the features of note. First of all, in these structures, we allowed the hydrogens simply to spontaneously refine their positions. It was possible to do that. And you can see here from this summation, these are average values for all the sp3 hybridized carbon CH bonds, 28 of them, sp3 hybridized CH2s, 10 of those, and then a series of aromatic or vinylic type of sp2 hybridized carbon. We had 112 of those in our data set. And these are the average values with their standard deviations. You can see that they're pretty precise. And moreover, they are not far away from the values you would get from typical neutron values. Now, these neutron diffraction data are not on our compounds. They are general averages as published in this paper by Alan and Bruno over 66, 136, and 184 examples. Not that much more than ours, to be honest, but they are not the same compounds. So they can make the direct comparisons, but we can assume that they are quite similar. Now, if you look at the bar graph, the histogram of our results, and compare that to the 99% confidence level for the neutron data, you can see that our histogram seems to be displaced a little bit towards the left, towards the shorter end of things. And indeed, most of these bonds distances are underestimating what would be given by neutron, but they're still within spinning distance, and actually within most of them lie within this 99 confidence level range, just a few outliers here and here. So we really have accurate placement of the hydrogen atoms. Now that we had expected, and we were very pleased that we could get that from these structures. But what we had not realized until we started doing this work is that in addition to placing the hydrogens accurately, we also got better structure data for the heavier atoms, in particular the carbon atoms. Now, Playton will calculate the bond precision, the average bond precision of the most abundant bonds in any given structure. And so for most organic compounds, that's going to be carbon-carbon bonds. And you can see here on the left, we have the values obtained by NoSpherA2. On the right, we get the average bond precision based upon the independent atom model done by an exactly parallel method. In fact, the values always get better with NoSpherA2, and the degree of improvement ranges from about 9% to above 70%. That was quite spectacular. So we are getting an average improvement in the precision of the structure of 42%. Now, there seems to be a correlation of this between to the data quality of the structure, the raw data quality, as well as to the final model quality. So both R1 and R8 monitor these values and tend to correlate with them. And here you see the data to parameter radials we were able to get from our crystals. Significantly, no structure was reduced in precision by this method, and furthermore, no significant discontinuities were observed. For me, that was quite important. What I mean is shown by this graph here. So it's a simple graph here. Here we have the percentage improvement in the carbon-carbon bond precision. Here we have the R1 values. So the lowest ones are here, the best structures that are here. And you see that for the best structures, we get a really good straight line correlation, very little scatter. But as you get to worse data over here, worse structures, then you get a little bit more scatter. Nevertheless, it is a pretty good correlation. We don't have points up here. We don't have points down there or down there. We have no outlier discontinuities, which suggest that something really weird is going on. We're seeing a general improvement, and moreover, the greatest improvement in precision always comes from the best quality structures. That we thought was a significant discovery. The second example are a series of organophosphines. These were being made in my lab by Flavia, the student who worked on this. And here's one of our best examples that we got from this. So here we have this very large molecule refined with NoSpherA2 to an R value of just over 1%, a featureless background map that's shown here, just a few small deviations in the model. And all the CH bonds accurately placed, and a full anisotropic displacement for each of those hydrogens. And what's also possible to do with NoSpherA2 is actually visualize the non-core electrons, the bonding electron density essentially, by this FC minus FMC map. So we've subtracted out all the atoms that are assigned that are not part of the valence level, and you can see therefore that you get maps of the electron density that correspond to the bond. You can see these pi bonds in the aromatic ring are displaced in this direction, whereas the ones in the alkyl bonds here, these are more cylindrical around the atom. We also see the lone pair on the oxygens, etc. So we are able to see the bonding electron density from a pretty routine data collection, whereas normally you would have to do very specialized diffraction experiments to very high resolution, and then have to do a multiple refinement to get this kind of result. Now, we don't claim that these are as good as a multiple refinement would be, but from the point of view of a chemist trying to visualize the bonding electron density to be able to get this kind of result with about an hour's worth of refinement work is a pretty fabulous result, in my opinion. We did altogether 17 of these structures, and most of them are even larger than the one I just showed you, because they have 3 of these bulky T-butyl groups on them. And again, you can see how beautifully we've refined all the hydrogen atoms to the anisotropic displacement, especially for these very motionally active T-butyl groups. And significantly, these molecules all have these phenolic groups which are involved in a kind of hydrogen bonding. And what you have to recognize is that all previous work of the IAM model for determining hydrogen bonding parameters required an adjustment, an artificial repositioning of the AH distances, because they are wrong from the independent atom model. This normalization procedure is always undertaken, but with NoSpherA2 it simply becomes unnecessary, and all the structures improved in precision. So here is the tabulation of the bond precision improvement, again using carbon-carbon, is the most abundant bonds in these structures. And we see here from 11 to 70% improvement. And here we see the data to parameter ratio and both the R-ins and the R1. And again, all the structures improved, none of them got worse. And you can correlate the degree of improvement up on the left here with the R's. In this case, the yellow ones are the raw data R values and the blues are the final model R values, but they basically follow the same line. The yellow and the gray correlation lines are similar. They are reasonable correlation, and they follow a general trend of a curve that goes a bit like that. I have omitted 4 outliers from this regression. They were outliers from the general trend, but notice where they are found. They are found here above the line, not down here below the line. In other words, for these outliers, we are getting a greater improvement in the average bond precision improvement than we ought to based upon the evidence of their structure. So we don't know exactly why these R values are low, and they're different for the refined models than they are for the raw data. But whatever the cause may be, we are still getting significant improvement in bond precision using NoSpherA2, and none of them got worse. A totally different kind of chemistry are these thiazyl chloride compounds. These have relatively few hydrogens in them, but I want to draw your attention to this one here, this methyl group. This methyl group is shown with isotropic hydrogens, and the reason it has those is because we refined this as a 2-part disorder model. There's nothing that unusual about a rotationally disordered methyl group at a low temperature crystal structure determination, but the important point was that with the quality of the difference maps that we had available, this was not at all obvious when we were working with the independent atom model, and it was the best solution with the independent atom model was simply to assign one geometry for these methyl groups. Yet when we put it into NoSpherA2, this immediately blew up because none of these hydrogens had enough electron density to refine properly for 1H. And so we went back and we improved the model, set up this disorder and refined it with a 2-component disorder rotation, and then it flew beautifully through NoSpherA2. So this is just showing you that we are getting a more accurate view of the electron densities, and hence we are more accurately able to model the structures. In this particular project, we were interested in both halogen bonding and chalcogen bonding interactions. Nevertheless, if you look at the complete crystal lattice, these interactions between these centers was also modified by the dispersion effects involving the hydrogens in the organic component. And so the correct placement of those hydrogens is relevant to these supramolecular effects. Again, we saw structure improvement, no structure got worse. Interestingly here is that the range is much smaller. The lowest was only 15%, but the highest was only 36%. So we have a higher minimum and a lower maximum improvement ratio. We have some ideas why it never got much better than 36%. We think it may have to do with the larger number of heavy atoms proportionally in these structures, and that's a hypothesis that we're still working on. And again, everything got better by something at least, and there were no discontinuities observed. A completely different set of structures were some work on hydrated copper sulfates. We got this structure by accident, this faintly blue crystal that we analyzed and solved, and turns out to be the trihydrate of copper sulfate. Now, I had never heard of this before, but it is a known compound. It's a mineral called bonatite, and it has a geometry that is fully consistent with a Jahn-Teller distortion of a D9 configuration of copper-2. So, fun result to get. Now, when you do NoSpherA2 on these kinds of structures, you have to think carefully about what you compute. And in this particular case, the best result, or the sufficient result to get good form factor calculations was to take the equatorial plane where the most significant chemical bonding is concerned, and so we could ignore these bridging sulfate ions. They're just symmetry equivalent versions of the coordinated sulfur here that's in the plane, but these form these long Jahn-Tiller extended bonds, and we could ignore those in the calculation. What we could not ignore is that copper 2 has a D9 electron configuration, so we'd have to specify a doublet electronic state in the calculation. But we looked this up in the textbook and found out there are in fact 4 sulfates of copper. The fourth one here is the pentahydrate we all know from our freshman chemistry courses. Notice that in that pentahydrate, only 4 of them are associated with coordinated to copper, and the other one is a water of crystallization. Here are all the crystals where we made of these compounds. We remade this trihydrate on purpose, and we measured it from the purpose-grown crystals as well. In the case of the anhydrous copper sulfate, there was no obvious way to distinguish one sulfur from another. First of all, let me just draw your attention to this, this 5th water in the pentahydrate. This is the one that is not coordinate to copper at all, but is only hydrogen bonded in the lattice. But for the anhydrous material, we ended up calculating the whole cluster with a 10- charge because there was no obvious way to differentiate one sulfur from another, but it worked. In the case of the monohydrate, we have here 2 different copper environments, so we had to capture all of those in the DFT calculation, and it turns out that this entity that I've circled was sufficient where we had a single bridging water associated with the structure. Importantly, however, here we have 2 different copper 9s which do not interact with each other, so that leads to an overall triplet state in the electronic structure calculation. And in the case of the copper sulfate pentahydrate, again, there are 2 unique coppers, and so you have to capture the 2 coordinating copper entities, plus you have to include this unique water molecule. And again, a triplet because there are 2 independent D9 coppers. For this pentahydrate, we had access to compare our result with this beautiful neutron diffraction study by Bacon. Notice how long ago it was done, but Bacon drew huge crystals where he used both regular water and deuterated water, and because deuterium and hydrogen have opposite effects in neutron diffraction, and combining those 2, the combination allowed him to beautifully define the positions of the hydrogens. Our NoSpherA2 comes close to that, and we've done a detailed comparison of all the hydrogen geometries and all the hydrogen bonding interactions, and we get very, very good matches from NoSpherA2 to what could be obtained from the best neutron diffraction data. And moreover, because we were working at low temperatures, we could get better definition of the heavy atoms than in this room temperature structure. And this simply shows that even with advanced quantum crystallography like NoSpherA2, we find that neutron and X-ray diffraction data remain complementary. We extended this notion of coordination compounds to look at some copper and nickel hydrated halides. So here's copper chloride hydrate. We did this in this by a comparison of data with a molybdenum and a copper data set, and we found we got better results with the molybdenum. Again, the key point here is placement of the hydrogen atoms and all the hydrogen bonding interactions. And again, we had neutron data that we could compare this to, and we got a very good result. For the nickel chloride, we again compared molybdenum and copper data set, and even though the molybdenum definitely gets a lower R value, the actual placement of the hydrogens and the accuracy of the hydrogen bonding was pretty comparable for both of them, as it turned out. Again, we could compare this to neutron data. The entities calculated in the copper state turned out to be the equatorial plane, ignoring the Jahn-Tiller distorted lengthened chloride systems, and so a doublet for a single D9 configuration. For the nickel case, we had to calculate the whole entity and one of the waters, which is shared in a 2-to-1 ratio between these molecules. And Again, because this is a high-spin D8 configuration, we have to use a triplet state, and again, that is described in the paper. A last example I want to give you is what I call a learning moment in NoSpherA2. It concerns two structures. First of all, this very congested phenol that the student was training on. So they were measuring the data, and I was doing it along with them, showing how it was done. And you can see it's a beautiful copper data set that could be refined by NoSpherA2, accurate placement of all the hydrogens and the hydrogen bonding. And then the student went on to make this related paraquinone, where we have further oxidation occurring, where this CH and now becomes a CO double bond, and this phenol also becomes a CO double bond in the quinone. And so we got beautiful structures. But then we made the mistake of doing one experiment too many, because I said to the student, look, you've got such a nice result. Why don't you remeasure the phenol with molybdenum? And she picked a different and, in fact, a smaller crystal on purpose. And we measured that with molybdenum data. And normally, molybdenum should get you better defined X-ray diffraction results. But they were much worse. It was clear that some serious disorder was going on, and we simply set this aside. Now, when I was writing up this work, I said, let's see if I can solve this disorder problem. And I was very, very pleased to be able to find that, in fact, it corresponds to 12% of this quinone incorporated into the lattice of the phenol. That makes it into something known as a molecular solid solution. And moreover, that solid solution fully obeys Vegard's law, which is the long-standing law for solid solutions and X-ray diffraction. Now, that's all well and good. This was completely unnecessary, lovely to do it, but we got the full disorder model refined with NoSpherA2, but we had the two good structures of the pure compounds as well, which are chemically the more interesting, except for this issue of solid solution. But the learning moment is this. I was thrilled to be able to find the second carbon and oxygen and notice that they are bent out of the plane just like in the quinone. And I simply refined the model like that, and I left the phenol alone. Now, in the independent atom model, that just sails through, no checks of alerts, nothing. Beautiful structure, because by ignoring the part occupancy of this phenol, and we're just talking about 10% of one hydrogen. I mean, that's nothing in the independent atom model. But if you do quantum mechanics, you can't have parts of molecules. You can't have parts of atoms. So this blew up in NoSpherA2, and I investigated why it had blown up. And I said, I've been a very silly boy. I did not give the right part occupancy for this phenol. And when I corrected that and applied some restraints from the known structures for the CO double bond and the CO single bond, then that oxygen spontaneously pulled out of the plane to get the true geometry of the quinone without any further ado. And this disordered model, fully refined in NoSpherA2, ends up being a beautiful structure. The point is that the precision of NoSpherA2 and the accuracy induced by the quantum mechanical calculations actually improved my crystallographic, the quality of my crystallography. I became a better crystallographer for this structure model because I had paid attention to the quantum mechanics and got the disorder model more correct. What are the prospects for higher NoSpherA2? That's a very important question. I'll have to say, I think the prospects are outstanding. It's a superb piece of software. I thought I'd start by just quickly going through my experience-based protocol for using NoSpherA2. I won't go through this in great detail because we published that in detail. This workflow is published in the Crystals paper, because there's some reviewers asked for it, and we're very pleased to supply that. Basically, this is the series that we go through. One point that did become apparent in our work is that atom labels are really important here. Now, in the independent atom model, the only thing that identifies this as an oxygen is this number 3 here. The label can be any text. You can call it anything you like. It doesn't have to be called O1. You could use your children's names, for example, 4 characters long. But in NoSpherA2, we're doing DFT calculations where each atom has to be individually labeled. And so now we are using the atom labels to identify atoms. And this cannot be changed easily. And so what we found out by hard experience is that you must get the atom names correct at the beginning, at the end of the full IAM refinement, and before you start NoSpherA2. Otherwise, you end up having to redo a lot of your work, and you may not get to the same endpoint in the repetition. For this and other reasons, we always implement NoSpherA2 in a copy of the original folder. That's really easy to do in OLEX2. It takes seconds and doesn't take up a lot of space on your computer. We therefore always keep the original independent atom model refined with OLEX2.refine available in the separate folder. And in fact, with 2 clicks of the mouse, you can jump back and forth between the two in OLEX2 and keep a live comparison of the independent atom model and the NoSpherA2 refinement as it develops. And that's really, really nice to be able to do. And moreover, should you make a mistake, you can go back to a well-defined model, improve the labels, and then redo it with a minimum of hassle. So that's important. Again, we have to obey the laws of quantum mechanics, and we follow the exact procedure that is outlined in that flowchart I showed you earlier. So, has a new era in chemical crystallography arrived with the development of NoSpherA2? I think it has. I imagine a future where data collection will be based on crystal quality. You will therefore collect a crystal, do a solution and a preliminary refinement, and it's either going to be a super low quality structure that you sort of siphon off at this point here, or you collect a full data set looking for a good structure determination. There will be specialized cases where you stop at the independent atom model level, and that's things like doing charge density refinements, using multiple methodologies, etc., where essentially you take the model with the independent atom and then you do post-structure analysis of that model. But for all the rest, the standard samples that are reasonable quality, you can routinely employ NoSpherA2 for using custom scattering factors. So what I suggest is that you employ custom atom scattering factors as a standard routine for single crystal structures. For low quality data sets, you will still have to retain the A-fix treatments for standard hydrogen geometry so that the methyl groups don't get wonky, for example. However, you must adjust the distances within the A-fix parameters to those for neutron data that makes the structure compatible with NoSpherA2. Once you've done that, you can then explore systematic relaxation of constraints. First of all, positional restraints, and then if you have enough data to parameter ratio, displacements can also be refined. And you simply stop this procedure at the no gains frontier. When things don't get better, you stop and you report the results. The one thing I would recommend is that any hydrogen atoms involved in hydrogen bonding get selectively treated to absolutely try at least to get refined positions and preferably also displacements for those hydrogens that are involved in hydrogen bonding, because they're so important that we get their bonding right. How can the use of NoSpherA2 be expanded? I do think that not enough people have picked up on it yet. There's great potential here, and I think it's being underutilized at the moment. Some of the barriers might be, first of all, that synthetic chemists tend to be quite conservative regarding crystal structures. That gatekeeper analogy I gave you is not simply a joke. Chemists might be unwilling to risk reviewer criticism about the included structures that might hold up their publication or cause it to be rejected. So that is a serious worry. At the same time, however, it is obligatory for all who publish structural data to be concerned about achieving the best possible structural position from the available data. It simply is not acceptable to throw away data that you have measured that is capable of giving you a better result and ignoring it simply out of convenience. The correct placement of hydrogen atoms, especially in the case of hydrogen bonding and other supramolecular structures, is crucial for chemical structure. Now, I have found as a PI crystallographer that I have tremendous flexibility in how I publish my results, and I've had surprisingly little pushback on my NoSpherA2 structures. I do always make a point to explain carefully what I've done and give the rationale for it and give sufficient references. So I explain myself well, but after that, there really has not been much pushback. Service crystallographers, on the other hand, may face challenges from unwilling clients simply because of these publication fears that they're having. That is a barrier that will have to be overcome. Among crystallographers, I think unfamiliarity with OLEX2 Refine is probably going to be a contributing factor. It was a factor for us, for sure. But we found that the software is well worth the learning curve because it is a modern piece of software that is undergoing constant improvement. So new features are coming out, and so there's a bright future for this method that parallels that of NoSpherA2. I would remind listeners that there was similarly early resistance when in 1997 the new version of ShellX changed to refinement against F squared rather than F. Every other software up to that point in time had used F, but Sheldrick moved to F squared. Now that resistance was eventually relatively quickly overcome, and because it gave better results. And it may very well be that the reason is that the current versions of ShellXL have really dominated structure determination. I think more than 90% of current structures are being refined that way, partly because of that change to the S squared model. So the improved results will lead to acceptance by the community. I do think a community response will be needed. I think there should be a development of some sort of standard protocols for the use of aspherical atomic scattering factors, independent of which software you use per se, but that users can point to those protocols and say, I've met the protocols, and that should lead to full acceptance of their results. Eventually, one might hope that automated validation software like the Platon CheckSIF would fully take into account the peculiarities of both NoSpherA2 and OLEX2 Refine, which are currently rather ignored, and that too should help with widespread and eventually even default implementation of NoSpherA2. Okay, some conclusions. In our experience, the NoSpherA2 has been demonstrated to work well for a large range of different small molecule structures. I've shown you organic examples, metal organic example, non-metal metallic phosphines and things like that. I've shown you some Thiazyl main group compounds. I've shown you conventional transition metal coordination compounds, and in each case, the results are comparable. There is a significant improvement in the average position of the interatomic distances in the models. There is a direct correlation of quality of data with degree of improvement, and that is not insignificant. In other words, why bother to grow good crystals if you are not going to use the results? This is a real motivation to keep growing the best possible crystals, and for our students to grow the best possible crystals, because there's a big payoff with good crystals. Good quality of data leads to superb improvement in precision of structure. There's this smooth transition to marginal improvement as the data quality gets worse, which is the mark of a robust theoretical model that works well and doesn't cause you any worries, and no evident errors introduced by NoSpherA2 if you apply it in a reasonably conscientious manner. At the worst, by trying it, you've only wasted some time, and you might go back to the independent atom model after all. The main restrictions we have encountered is with very complicated structures, particularly too much disorder or too many degrees of freedom. Here, the DFT calculations can simply become overwhelmed, and the ability of NoSpherA2 to actually calculate the structure factors fails. That does happen. Of the CF3 structures, many disorder components, for example, I do think that the retention of positionally adjusted affix restraints for poorly behaved CH structures and even CF3s, like I mentioned in my protocol, is really advisable. So, in summary, we think that this improvement of average position of the structure simply says it all. If that's the case, then we really should be doing this and not just ignoring it. So that NoSpherA2 is available, it's easy to use, it's free, and it really deserves to become the default way for refining routine chemical crystallographic structures at the current time. Okay, with that, I come to the end, and I thank you for your attention.